the trigonometric functions and their derivative, and we saw some applications of differentiation and their properties in those situations. Now we'll continue ahead with differentiation of some more types of functions. Okay, so for example, today we will take a look at exponential function and natural log function and their derivatives respectively. So first of all, let's look at the formula set of derivative of all trigonometric functions. Last time and before that, we have discussed about sine and cos. So similarly, just as we have the formula for differentiation of sine and cos, we have the formula for differentiation of 4 other simple trigonometric functions. So let's talk about them first. So derivative of trigonometric functions. So we start with the two that we are familiar with. Differentiation of sine x is cos x, and derivative of cos x, as we've seen, is minus sine x. Now the additional formula, derivative of tan x, is given by sec square x. Okay. Then derivative of cosec x is minus cosec x cot x. Okay. Derivative of sec x is sec x into tan x. And finally, derivative of cot x is minus cosec square x. So this formula table completes the list of derivatives of all 6 trigonometric basic functions. Now obviously for us in physics, the most commonly used functions are going to be sine and cos. So these are the formulae that will need the most out of this, but at the same time you should be knowing these other 4 formulae also. So now for example, from this we can solve something like this. Suppose we have a function y is equal to, this is sin x plus cos x upon sin x into cos x. And what we want to do is we want to find the derivative of this function and find the value of dy by dx at the point x equal to pi by 6, let's say. So what we have to do is make use of the derivatives of these trigonometric functions. But before that, we have to also simplify this equation in such a way that we get it in terms of what the formulae are. So as you can see, we need to simplify this sin x plus cos x divided by sin x cos x into a combination of simple terms. So the algebra we'll use over here is that if we have something like this, a plus b upon cd, we can always write it as a upon cd plus b upon cd. So we'll start with that step. So we can see that
sin x cos x plus cos x upon sin x cos x, right, Mr.?
Yes. Okay. So first step, correct. So when we divide this, sin x upon sin x into cos x gives us sec x, right? And from above you can see that the derivative of sec x will be sec x tan x. Whereas the second term will be cos x upon sin x into cos x. That will give us cosec x. So this is 1 by cos x.
So you have wrote x is equals to pi upon 6.
Yes, pi by 6. Yes, that's correct. Pi by 6 is the same thing as 30 degrees. Okay, in
Yes.
radians. So further, 1 by cos x by definition is sec x, right? And 1 by sin x by definition is cosec x. Okay. So we can also define the function in a simplified form as this now, that y is equal to sec x plus cosec x. So once we have done this, now we are ready to apply the differentiation formula from above. So this means that
Sir, sec
differentiation of
x plus cosec x, how you wrote?
1 upon cos x is defined as sec x, right? And 1 upon sin x is defined as cosec x.
Okay, sir.
So those are the definitions of. So if you go back to basic trigonometry of right angle triangle, you'll recall that if this is theta, then you have sin theta is perpendicular upon hypotenuse. Cosec theta is what? Hypotenuse upon perpendicular. So cosec theta is 1 upon sin theta. Like that, sec theta is perpendicular, I mean hypotenuse upon base. So sec theta is the same thing as 1 upon cos theta. And like that, cot theta is base upon perpendicular. So the cot theta is identical to 1 by tan theta. So again, these are some basic things about trigonometry that you should know. So anyway, coming back to this now. So we have got y as sec theta, sec x plus cos x. So dy by dx becomes differentiation of this whole function sec x plus cosec x. Now we'll take the differential operator inside the bracket. So it becomes differentiation of the first term, that is sec x, plus differentiation of the second term, cosec x. And now the next step, we can just refer to the formula table above. So you can see from there that differentiation of cosec x is minus cosec x cot x, whereas differentiation of sec x is sec x into tan x. So this will finally become sec x into tan x minus cosec x into cot x. And that is our final answer. This is dy by dx. Then of course we'll substitute the value of x as pi by 6 also. We'll get the final numerical answer for this part. So we asked two things to find dy by dx, which we have found over here. We also have to find the value of dy by dx at pi by 6. So next we will do that. So you can just first note this down up to here.
Okay.
Sir, in the answer dy by dx is equal to sec x, and after what it is not even?
Should be tan x, should not be tan
Okay.
theta. That's correct. Be sec x into tan x. Huh?
Yes, so tan x.
Yeah.
Done, sir.
Okay.
Sir, 1 minute.
Yeah. Now see the final part of this question. So next thing we have to find. So one is we found dy by dx itself. Then second thing, we want to find the value of dy by dx at x equal to pi by 6. So we just substitute that over here. So sec pi by 6 into tan pi by 6 minus cosec pi by 6 into cot pi by 6. Okay. Now pi by 6, as you know, is the same thing as 30 degrees. Okay. So remember last time we were talking about that 30, 60, 90 triangle. So the ratio of these sides is what? Root 3 is to, sorry, 1 is to root 3. Okay. So from this you can see that sec is 2 by root 3 and tan is 1 by root 3 and cosec is 2 and cot is root 3. Okay. So this becomes 2 by 3 minus 2 root 3. And we can leave the answer this way. You don't need to further solve.
Done, sir.
Sir, 1 minute.
1 minute.
Yeah. So this one is our final answer for this part. Okay, done?
Yes, sir. Done.
Yeah. Yes. Yes, any doubt? Okay. So we come to the final two formulae of differentiation for functions. So we see exponential function and what is called natural log function and their derivatives. So first up, exponential function. That is given by the formula y is equal to e raised power x. Where e is called the exponential number. Okay. It is a constant which is also an irrational number like pi, for example. So the approximate value of e is 2.7. So the graph of the exponential function looks something like this. It has this kind of a behavior that, at x equal to 0, the value of y is 1. Y is equal to 1 at x equal to 0. Y tends to 0 as x tends to minus infinity. Whereas y tends to infinity as x tends to infinity. Yes.
It is integral or interior function.
Sorry, what come again?
So the
What's your
heading is
question?
integral log function or interior log function. What it is?
No, it's natural log function. It's neither integral nor
Oh, I
integral.
thought
It's natural. This term is natural log. Yeah, right now I'm not even talking about the log function. I'm talking about the exponential function. We'll come to that later. So exponential function, back to this, y is equal to e raised power x. E is a constant, which is an irrational number. Irrational number means that it is a non-recurring, non-terminating decimal number, just like pi. Okay. Its approximate value is 2.7, and y tends to infinity as x tends to infinity. So that is the nature of the graph, which you can see that the more you go on the negative side, the smaller the value of y becomes, tending to 0 as x tends to minus infinity. So for example, if you take x as minus 100, so y is e to the power minus 100, which is the same thing as 1 by e raised power 100. So, it's a very small number because the denominator is very large. So it's almost tending to 0. Whereas on the positive side, if you make x, let's say, a large number like 1000, so y is equal to e raised power 1000. That's a very large number. So it starts tending to infinity as x becomes large on the positive side. Whereas if
Sir,
y tends to 0 or it becomes smaller and smaller. Yes, beta, what's the question?
so you are saying that the larger the number is, the more smaller it will be in the graph.
No, I'm not saying that, beta. I'm saying that
It becomes
the y tends to infinity as x tends to infinity. So in place of 1000, if you have 1 million, then y is e raised power 1 million. So imagine e into e 1 million times. It's a very large number, no?
Yes, sir.
So,
Whereas if x is negative, yeah. So the further
so,
down you're on the negative side, the smaller the value of y becomes. Yes.
so I was asking, like, you have said that the value of E is approximately like 2.7. So if
Yes.
X is 1000, so then Y will be equal to 2.7 raised to 1000, like that.
Yes. Exactly. That is the meaning of power. Okay, x is the power of e over n. So as a simpler example, suppose we take the value of x as 2. So y is e square. So that means y is equal to e into e, or approximately 2.7 into 2.7. But similarly, suppose x is minus 1, then y is becoming e raised power minus 1, or 1 by e. That's approximately 1 upon 2.7. So from this set of values, you can understand why the graph has this kind of shape. So note this down first, then we will come to derivative of exponential function or differentiation of exponential function.
Completed, sir.
Right. Now let's,
1 second.
2 minutes, sir.
yeah, okay. So now let's come to derivative of this function. So this is a very interesting and important aspect. So exponential function has the unique property that derivative of e raised power x itself is e raised power x. Okay, so it is the only function in mathematics which has this property, that the value of the function itself is equal to the value of the derivative. So that's what makes this function important for applications in physics, which we'll see later.
So this is a formula we will be using.
Yeah, this is the formula of differentiation, right? Just like we've seen the formula of differentiation of x to the power n, or differentiation of sine x, cos x, etc. like that.
Okay.
So we are now coming to the end of the series of formulae. The last one will be after this, which will be the natural log function.
Sir? Sir? Sir?
Okay, people. So finished with this, I hope.
Sir?
Yes.
Sir, can you please explain the third and fourth example as to why in the third the value is 0 and in the fourth infinity?
1 by e to the power of 100 beta. So you can understand it's like 1 by e into e into e 100 times. No? It's a
Okay.
very large number in the denominator.
Achha,
No?
so it is as good as infinity, that's why it's 0.
Yes.
That's why y is 0. And
I
in
said
the
it's
fourth,
tending to 0. I didn't say it's exactly 0. It's tending to 0.
achha, okay. Tending to 0. Okay, fine. Thanks.
So like if you just multiply 1 by 2 into 1 by 2 only up to 100 times, do it in a calculator and see you will get such a small value. It's practically as good as 0. Okay? So like that here also it's e raised power 1000. So multiplying e with itself 1000 times. So it will be a very, very large number. No? It's like it's tending to infinity.
So,
Yes.
can you please explain that formula once? I was disconnected.
Which formula beta?
So, the one which is written in the black pen.
That's just write down the formula. No? It's differentiation of e raised power x is e raised power x. But there is no further explanation of that. This is just factual thing. Okay? Derivative of the function e raised power x or differentiation of the function e raised power x is e raised power x itself. Okay. Now let's come to the final formula of our series. Natural log function. So this term log is actually short form for logarithm. So supposed to be familiar with logarithms, but I don't know because of last year's situation in class 10th, how many of you have studied logarithms or not. So I'll just take you through the basics. Okay.
Sir, new term.
So it's new term for you. Okay. So if we say in maths
No,
that
sir.
log of x to the base b is equal to y, it implies that x is equal to y to the power b. This is the meaning of the term logarithm or log. Okay. So for example, so first of all, this quantity b over here that we write, that is called the base of the logarithm. So for example, if I say that log of x to the base 2 is equal to 3, and then I ask you that therefore what is the value of x? You'll understand it from this definition. Okay. That x will be equal to 2 to the power 3. That means x is equal to 8. Or for example, if I ask you,
To the power of 2, na? Y is to B is there.
oh, sorry,
3 to power
I
2.
made a mistake. I made a
Sir,
mistake. This is b to the power 9. Yeah, that's right. This is the definition of log. Okay. So this is the definition of the operation. So for example, if I ask you that log of 1000 to the base 10 is equal to n. So find the value of n now. Can you tell me how much this is?
3.
10 to the power
Yes.
3.
Very good. No, so 1000 is 10 to the power 3. That means the value of log 1000 to the base 10 should be how much? It should be 3. Okay, so this is the basic idea of log. Okay, so what we understand here is that 1000 should be equal to 10 to the power n. So 10 to the power 3 is equal to 10 to the power n. That means n is equal to 3. So I'm coming to natural log also. I'll explain to you why we use the term natural log for this particular one. But first of all, the general definition of log. That is this one. Okay.
so this we have to solve.
Yeah, this is for you to solve now.
Okay.
So just solve this and send me the answer of exercise of example 1 and 2. Nobody got the answer of example 1 yet?
0.5.
Yes, very good. That's correct, Beta. Very good.
So 0.5.
Yes, 0.5. Just work it out and send me in the text message.
Sir, 0.5.
Yeah. Now everybody knows, but just send it to me in text message. Second one. Yes, very good. Sanvi, Bhaumik, correct. Siddhant, correct. Veer, correct for the first one. Still waiting for the second one. Rishita, correct. Good. Okay, so this one's answer will be 0.5 because you know that 0.25 is equal to 0.5 to the power 2. And this one's answer will be 100 because you know that 0.01 is 100 to the power minus 1. Okay. So this is the general definition of the term logarithm. Okay, or what in short form we call log. You might have seen these things called log tables. Any of you are familiar with log tables?
Yes, sir.
Yes,
Yes,
sir.
sir. No, sir.
Acha. Okay, so you will see at some stage. Okay, and basically in many ways it's a relic from the past because you know before people had handheld calculators, you know, or now you don't even need calculators because everybody, like all working professionals, have powerful laptops which can do all sorts of calculations, not just simple arithmetic and scientific calculations, but even write lengthy programs for doing like problem solving. But before that era, before you had softwares for doing your engineering design and all that, even basic calculations, there were no calculators available. So log tables and logarithms were used to do complex calculations. So it's a relic from that era. Anyhow, now we will see two special cases of the log function. One is called the standard log, or you can think of it as a log function or a log with a standard base. And the standard base is in keeping with the decimal system. The standard base is 10. Okay, and the symbol used for standard log is just log. If I don't specify any base and I use the symbol log log, then it means that I'm talking about the standard base. So for example, log x, what does it mean basically? It means log of x to the base 10 because this is basically standard log. This symbol is standard log of x, okay, or log of x with standard base. That's it. Okay. So for example, once again, if I ask you what is log of 0.001, okay, then we should understand that first of all we are talking about log to the base 10 of 0.001, and if that is equal to x, that means 0.001 is equal to 10 to the power x. So you can see that x is equal to -3. So one is this thing, standard log. The other is natural log. So natural logarithm, the symbol that we use for that is ln. It stands for natural log. So natural log is log with base e, where e is that exponential. The one we just saw, an exponential function. E is the irrational number whose approximate value is 2.7. So ln x is basically log x to the base e. Okay, whereas log x is basically log x to the base 10. Log log x without any base specified. That means we are using the standard base of 10. Whereas ln x means that we are using the natural base, and the natural base is the exponential.
Sir, sir, if there is no base, so we have to take base as 10, no?
If there is no base and the spelling is log, then we have to take it as standard base. But if the spelling of it is ln, then we have to take the natural base. Understood? No?
Yes.
Whereas other than 10 and e, if we want to use some other base, then we will have to use for any other base capital B,
Sure.
let's say, we have to use this symbol. We have to take the base separately. So for example, if I want to express, just a moment, beta, log of 20 to the base 4, okay, then I have to express it this way. Log of 20 to the base 4. I can't just leave it as log, because log alone without any base will mean that we are talking about the standard base, which is 10. Yeah, what was your doubt, beta?
So I just want you to explain that that one. ln x is equal to log of e.
Ln is the symbol ln stands for natural log. The n stands for natural, L stands for log. And natural log means that we are taking the base of the log as the exponential number. Okay? The base is 2 points, that approximate 2.7 exponential number.
Thank you.
It's clear, no?
Yes, sir.
So basically, for example, if we want to calculate ln of x is given to us as 3. So that means x is basically what? It is e raised power 3. Okay. Or we want to calculate, it's given to us that ln of e square is equal to 2, is equal to y. So find the value of y. So here we can see that e square is equal to e to the power y. So y is equal to,
Sir, in natural log,
yeah,
sir, what you wrote LA, sir, in the third line, sir.
log with base e.
Log with
Natural
this
log stands for log with base e. Okay? The value of the base is the exponential number e.
Sir, symbol is LX or LR?
Ln beta, ln. L for log, n for natural.
Okay.
This symbol here, no? This is ln x. Or in short, we can just write it. Even the x without the bracket is fine. It's understood that it's ln operating on x. So this basically means what? We are operating log with the base e on x. Okay. So for example, if this is given to us, that means what is the value of x in this particular example? The value of x must be e raised power 3. Or if it is given to us this thing that ln of e square is y, then what is the value of y? So it implies that y is 2.
Sir, in the second example of natural log, I did not get how you got y is equals to 2.
Okay, so see, basically, when we express any log like this, the general expression is what? If log of x is y and the base is b, it means that x is equal to b to the power y. What it now? Now in this example,
sir.
what is my x? My x is e square. What is my base? It is e. And what is y we want to find out. Okay, so just replace it. So e raised power 2 is equal to e raised power y. So compare the two sides. What is y's value? It's 2.
Yes, sir.
What?
Sir, down that which you wrote with black, it is for any other box B, right?
Yeah, sorry, beta. What was your question again? Yeah.
I was
Yeah,
asking
what was,
down one you wrote for any other box B.
for any other base, beta.
Base.
Any other base. Any other base B, we have to specify the base's value like this. So for example, if I want to express log of 20 to the base 4, I have to specify the base separately as 4. If I leave the base blank over here, it means that I'm talking about base 10. And if I write ln, it means that I'm talking about base e. So that's just a matter of symbols. Understood? No?
Okay, sir.
So what happens is, like in pure mathematics and also in like complex calculations in things like engineering and all, we tend to use standard log more often. Whereas in physics, the nature of the functions and all we are dealing with is such that we use natural log more often. Okay. So in our physics portion, whether it is like intermediate level physics or even higher physics later, if any of you study, you'll see that this becomes the most important application of the log function, the natural log function. And one of the reasons for it is actually that this number e is that special number. Why it is special? Because exponential function has this property, which I told you about earlier. That is the only function in mathematics which has this property, that the derivative of the function is itself. Okay, so e has that special property. Hence, when we take log to the base e, or what we call natural log, we have a special kind of function. Okay, and that's why it's more useful in physics. So at our calculus level, this was just background information, what I told you. At calculus level, what is important for us is derivative of which function? The natural log function. We will not worry about the regular log or any other, the standard log or any other base. We will only be concerned with natural log function from this point onwards. Okay. So derivative of natural log function, or in simple terms, what we from now on call ln. So differentiation of ln x with respect to x is given by the formula 1 by x. Okay. So now we have a complete list of formulae that we require for differentiation. Starting from differentiation of x to the power n, which we learned on the first day, we talked about differentiation, and going through the 6 trigonometric functions we talked about today, then the exponential function, and finally the natural log function. I think it's a total of about 9 formulae that you have to keep in mind. So if you are able to recall these 8 or 9 whatever formulae without any difficulty, then you will not have any trouble with the application of differentiation. And with practice, you will be able to recall. Just a matter of working out enough questions. So initially, you might have to make a table like this and keep it alongside while you're doing questions and refer to it. But with practice, you would have done the repetition so many times that you won't need to refer to a table of formula anymore. It's always good to write your formula in a like compressed kind of space. It makes you feel happy that it's very little because it's fitting in a small space. So effectively, everything that we've discussed is compressed down to these 9 formulae. So let's look at an example.
2 minutes.
Yeah.
Done, sir.
Okay, so try out this question. Okay, very good, Rishita, that's correct. Both your answers are correct. Sanvi, correct, very good. And Manas, correct, very good. Yeah, so far 3 people have sent me the answers. Okay, so let's work this out. So the function is given to us as you can see, it's a combination of two terms, an exponential term and an ln term. So we'll have to use property of differentiation to find the derivative of the function. So when we differentiate the whole thing, becomes differentiation of e raised power x plus of differentiation of this, but that -2 is a constant, so you can bring it outside. So into differentiation of ln x. And that's it. Once we have, so this is the property of differentiation that we use from this step to this step. Once you've done that, rest is formula. So we have seen above, exponential functions differentiation is e raised power x, whereas ln functions differentiation is 1 by x. So our answer simply becomes e raised power x minus 2 by x. That is the derivative of the function. This is the value of dy by dx for the given function. So this is the first part. Now slope of the tangent. So what we mean by slope of the tangent, as we've seen before, if now I don't know how this function's graph looks, so I'm just, yes,
तो आपने बस वो वैल्यूज पुट की ना
yes, exactly. Okay, so now at a particular point, let's say x equal to x1, I want to find the slope of the tangent. This is my tangent line, so its slope will be equal to what? Will be the value of dy by dx at that point x equal to x1. Okay, so slope of tangent at a point, let's say x equal to x1, is nothing but the value of the derivative dy by dx at that point. So that's what we have to apply over here. So this is the dy by dx, but we want to now find its value at which point at x equal to 1. So this thing will give us, this will be what we are looking for. This will be the slope of the tangent at the point x equal to 1. So substitute the value of x in this as 1. So it's e raised power 1 minus 2 by 1. So as you can see, it's e minus 2, which will be approximately 0.7 because e is approximately 2.7. Right? So, okay,
So this graph you randomly made.
I just randomly made it. I didn't set that for this is a general situation. Okay, so for this particular function, this is. So in general, for any function, y is equal to fx. Okay, this is the concept. Slope of tangent at a particular point is the value of dy by dx or the value of its derivative at that particular point.
So can you please wait? I want to
Yeah,
understand.
sure. So these are just few examples to show you that how the concept of slope of tangent, then the application of properties of differentiation, like taking the differentiation operation into a bracket which has a sum or difference of terms like this and all, that all remains the same. Okay, it's just depending on what type of functions we have to apply the particular formula. Exponential function, logarithmic function, trigonometric functions, along with, of course, the most important and basic one, which is differentiation of x to the power n. Because most often the applications that we'll be doing will be of algebraic functions in which we are using those formulas.
So ये second वाला एक बार explain कर दोगे please?
Yeah, so see, in second part, what we have to do, we have to find the slope of the tangent at the point x equal to 1. Na? So how we find the slope of the tangent? By finding the value of dy by dx at that particular point. So what is dy by dx? Is this function, right? So now we are finding the slope at which point x equal to 1. Na? So in this function, क्या substitute करना है? X के value को 1 substitute करना है. So just substitute x as 1. So we get e minus 2. And e is approximate
अच्छा,
value.
okay, sir, I got it.
Just like that question we did earlier today where x's value was pi by 6. That sec x minus tan x, something like that we did. No? So
Yes, sir,
finally
yes,
the
sir.
derivative we substituted 30 degrees, which is same as pi by 6. So like that, same thing here. Only difference is now we're talking about exponential function and ln function. These two things.
Yes, sir, thank you.
Okay. Okay, so now we have all the tools for
2
finding
minutes.
out.
So could you just put up 1 minute? 1 minute.
Yeah, sure.
Done, sir. Thank you.
Oh,
1 minute, sir.
okay. Okay.
So you're going to send these notes on the.
Yes, I will send them along with the recording as always.
Okay, sir.
Okay. So with these kind of things, now we can solve simple functions derivative very easily using all these properties and these formulae. Okay. But now we'll look at some slightly more advanced properties. Okay. So far along with the formulae, we saw the 8 or 9 formulae already earlier. We've also seen some basic properties. The properties of differentiation we saw earlier. This is what we've been using till now. We saw that, oh, just a second. Yeah, so we saw that we have this property that differentiation of any constant is 0. That was the first property so called. Then differentiation of a constant multiplied by a function. And all this we have used today also. So you are all familiar with this. Okay. Now we'll see some more slightly advanced type of properties. So the third property we had seen was the distributive property. Differentiation of the sum of two functions is sum of their derivatives. Just a minute. Yeah. So these are all things that we've seen. Or even if there's a minus sign in between over here, we can put a minus sign there. Now we'll come to more advanced properties. But before that, have I taught you the short form for differentiation using the prime notation?
Yes, sir.
You are aware of this now?
Yes, sir.
Good. So this is the shorthand notation for derivative. Okay. So now next thing we'll see in the advanced properties.
So in the third form, the plus minus is optional or
No, it's like if the sign is plus, then the sign here is plus. So for example, suppose I'm doing differentiation of x square plus x cube. Then it will be differentiation of x square plus differentiation of x cube. Understood now? But suppose I'm doing differentiation of, let's say, sin x minus cos x. Then that will be derivative of sin x minus derivative of cos x, like that.
so it can be both case.
Yeah, it can be either case. If it's plus, then the sign here will also be plus. If it's minus, then the sign here will also be minus. You know, simple. Okay, now in the advanced properties, it's part of the same series, but now we are coming to the advanced ones. This one is called the product. So if a function is the product of two functions, I mean, if y is the product of two functions, okay. So for example, if y is suppose x square into e raised power x, so you can see it's the product of two separate functions. Okay, one of them being x square and the other being e raised power x. And we can't simplify it further. Suppose it had been x square into x to the power something like x square into x cube, then we could have simplified it. But this is x square into e raised power x. So we can't simplify it. Or for that matter, for example, if it is y is equal to sin x into cos x. Now, some of you studied some trigonometry, you can see that maybe you can write it as sin 2x divided by 2. But as of now, again, this is a product of two functions. Fx is sin x and gx is cos x. And you can see y is fx into gx. It's the product of two functions. So how to differentiate? Okay, so that's what the
This is
product
the
rule is.
example of product rule.
No, we haven't come to product rule yet. This is an example of a function. These both are examples of functions which are product of two functions, functions of this type. Okay. Now we come to the product rule. Now, what is the product rule? That differentiation of such a function will be given by this formula. First function multiplied by derivative of second plus derivative of first function into second function. So this is the product rule formula. That if a function or if y is the product of two functions f and g, then dy by dx or the derivative of y is given by this. Okay, so this is the statement of the product. Okay. So let's apply this to this example now. So y is equal to x square into e raised power x. So dy by dx will become first function into derivative of second function, that is fx into g prime x, plus derivative of first function, so that is differentiation of x square multiplied by the second function, so that's e raised power x. Now you apply the regular formula that you know. So
Sir, in the
differentiation of
first
e raised,
part in that bracket, it won't be e raised to x,
which
dy
one?
by dx, x square into dy by dx, e raised to x.
Yes, sir, even I am
Oh, sorry.
doubtful.
Yeah, that will be e raised power x. And that's why you can see that below I have written x square into e raised power x, because we know that the derivative of e raised power x is how much? It is e raised power x only. Now. Okay, now it's all right now.
Yes, sir.
Okay. Now second term क्या हो जाएगा? Differentiation of x square is how much?
Sir,
What is different?
2x.
So 2x into e raised power x, and we can just simplify it further one step by taking e raised power x common. So now we can see that for this particular function, the derivative of the function dy by dx, we had to use the product rule, and by that it came out to be this. Okay. So write down the product rule and this example, and next work out for this one. For this example, work out the value of dy by dx. Tell me how much that is.
So 1 second, can you scroll up?
Yeah, but those properties we've written earlier also. That is
No,
just
sir, I want to see the short form ones.
yeah. Acha, that f prime is the short form for derivative of fx.
Sir,
Yes.
sir, why we not the differentiated x square first?
We have differentiated ना बेटा, देखो यहाँ पे क्या differentiate?
सर मैं
We are
अब उसके पहले क्यों नहीं किया मतलब वो
because
x square
that's
तो
not the formula ना, see the product rule formula बेटा, it is fx into derivative of gx plus derivative of fx into gx. तो यहाँ पे fx क्या है? x square है. Understood now ना?
हाँ yes sir, sorry sir.
So g is d upon dx.
Sorry.
So instead of x square into in formula it is written f of x into gx. So after solving here in bracket you have written instead of g d upon dx. So it's the substitution of it, or
It is a substitution of it, no?
so in every sum we have to do that.
Yes, you have. See, that's how I've applied it in this one also. Differentiation of, in the example I've done over here in the red, differentiation of x square e raised power x. I've just substituted, na? Fx is x square and gx is e raised power x.
Okay.
Understood the example, na? Go through the steps once.
Yes, sir.
Okay. Yes, very good, Rishida. That's correct. Yeah, Sanvi, correct. Manas and Swam, think what you sent is correct, but it's like the way you typed it. Okay, anyhow, let's go through the steps for this example. So it's the product of two terms, sin x into cos x. So differentiation of y with respect to x will become first function multiplied by differentiation of second function plus differentiation of first function multiplied by the second function. Now you must have realized by now one thing, that it doesn't matter what order we write this in, because we're adding two things now. So we can write it in reverse order also. I can write differentiation of first function into second plus first function into differentiation of second. I can interchange these two. It will make no difference to the final answer. So sin x into cos's derivative is minus sin x. So plus sin's differentiation is cos. Okay. So cos into cos. So ultimately, as you can see, this becomes sin minus sin square x plus cos square x, or we can write it as cos square x minus sin square x. This is the derivative. So Manas, I think you also meant to write sin square only instead of sin 2x. Okay. So
Sir, here d upon dx sin x plus d upon that distributive property we will not do.
नहीं बेटा, because it's not the sum of two terms, ना? It's a product of two terms. Distributive कब use करेंगे? When it had been something like this. Suppose y had been sin x plus cos x. Then we would have taken the differential operator directly inside. Yeah?
Okay, sir, sorry.
So that's why that is the distributive property. This is the product rule, because it's a product of two functions.
So how did you got cos square x and sin square x?
Sin x into sin x कितना होता है बेटा? Sin square होता है ना?
So can you explain with the second last one?
It is minus sign or
What is differentiation of cos x? Tell me.
sign
No, it's minus sign.
minus.
Okay. So this term is becoming minus sign, na?
Yes.
So now what is sin x into minus sin x? It's minus sin square x. Similarly, what is differentiation of sin x? It's cos x.
Got it.
So this term is cos x. So this cos square x term is here now.
Sir, okay, got it. Because you interchange the position, so I got confused.
Okay. It's the same thing, na? Writing a minus b is the same thing as minus b plus a.
Yes. Got it.
Completed, sir.
Okay.
Sir, 1 minute.
Done, sir.
Okay. All right. Now, the fifth and final property. So these two are the advanced properties. This is called the quotient rule. This one is a bit complicated. If y is expressed as the division or the quotient of two functions, then dy by dx is given by this rule. It is denominator multiplied by differentiation of numerator minus numerator multiplied by differentiation of denominator divided by the denominator whole squared. So you will have to get used to memorizing this formula and applying it. And you have to be very careful because here you can't interchange the two terms in the numerator. There's a minus sign in between. So if you interchange it, your answer will come out to be wrong. So before we write this down, let's just look at a quick example. Suppose y is equal to x square upon sine x. Right? We want to find dy by dx. So we will use this rule over here. That dy by dx will become the denominator into differentiation of the numerator minus the numerator into differentiation of the denominator. The whole thing divided by the square of the denominator. And then we solve this further. So differentiation of x square is 2x. Differentiation of sin x is cos x. And sin x whole square is one and the same thing as sin square x. Now we can see that we can simplify this a little and write this as 2x sin x minus x square cos x, whole thing divided by sin square x. We can simplify it further also, but at the moment I'll leave it at this. So write this down and try out one more example yourself.
Sir, this is the quotient rule formula.
Yes, this one.
Okay.
Okay, so finish writing this down and then try out this example. Yes, very good. Rishita correct and Sanvi correct.
For example, why why instead of x square you wrote 2x?
Come again, beta. Where in place of x square we wrote this?
Sir, in this example,
In this example, वो differentiation है ना बेटा? Is the differentiation of fx ना? So it's 2x ना? See this term is derivative of the numerator na?
so
Understood?
why
Na?
not in x square or after minus?
Because यहाँ पे fx है. It's see gx into f prime x minus fx into g prime x.
So
You have to
when there
apply
is
this
prime
formula.
only, then only we have to use.
Prime stands for derivative na beta. What is f prime x? Is the differentiation of fx. What is g prime x? Is the differentiation of gx. Got it now?
Okay, got it.
Okay, so let's apply this quotient rule concept over here. So y is one function divided by another. So dy by dx will become the function in the denominator multiplied by the differentiation of the numerator minus the numerator, which is 4x, multiplied by differentiation of the denominator, which is 1 plus x squared. The whole thing divided by the denominator squared. So 1 plus x squared whole square. Now we have to do a bit of algebra here. So this is 1 plus x squared into 4. So this derivative will be 4. And this derivative will be 2x. So minus 8x squared. So this will become.
So in this case, the 4x will be only 4, no?
Huh?
The 4x was there, no? So by the prime one, that
तभी तो 4 लिखा ना
it will be only 4.
4 ना तभी तो यहाँ पे 4 लिखा था, right? This is 4
Sir.
ना?
Sir,
Yeah.
can you explain how you got the derivative like of 1 plus x square?
Very simple. Take the differentiation operator inside. So what is the derivative of 1? Tell me, beta, what is the derivative of 1? 0. And what is the derivative of x square?
Sir, 2x.
So हो गया ना? Got it?
Yes, sir.
Understood now?
Yeah.
Okay. Yeah.
Before doing that dy by dx, we can take that 4 outside, right?
Yeah,
That
we
won't
can
make
take
a
it.
difference.
Correct. In fact, that's the better thing to do. Right? It just makes the whole thing easier. It's a better method that you take the 4 already outside before differentiating. That's why you see in the answer we have a 4 outside also. So all of you understood this. This is going to make it easier to actually handle the whole thing because you're directly taking the 4 outside. So dy by dx, just take 4 outside and then differentiate this term. This just makes a little bit easier to handle the whole thing. Then you proceed with this. So denominator into differential of numerator.
So in that case, one will get cut by the derivative in फर्स्ट फोर
1 कट क्यों होगा बेटा? वो टर्म कॉमन नहीं है ना, देखो अभी सॉल्व करेंगे आगे.
सर नो 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 अबाउ
हाँ
पहले का सामने सर, तो उसमें 1 प्लस एक्स स्क्वायर था ना, तो उसमें आपने 4 को 1 के साथ मल्टीप्लाई नहीं किया, तो इन द सेंस 4
4 को किया ना 1 के साथ मल्टीप्लाई. ये 4 कहाँ से आया रमेश बताओ? ये किया ना 4 को पूरा 1 प्लस एक्स स्क्वायर से मल्टीप्लाई.
सर उससे नहीं सर, इन द राइट हैंड साइड पार्ट where 8x square is there too.
हाँ
तो उसमें 4x आएगा ना, 1 प्लस एक्स स्क्वायर था वहाँ पे.
अरे 4x स्क्वायर माइनस 8x स्क्वायर ही तो डायरेक्टली माइनस 4x स्क्वायर आया. You didn't understand the step. That means okay. You open this bracket na, it's 4 plus 4x square minus 8x square.
So no, not that one.
So then
Sir,
what?
here.
The step before that, what? अरे उसका डेरिवेटिव भी तो 2x बेटा. I explained now what is differentiation of 1 is 0 ना.
Okay, so differential of 1 is 0.
Obviously 1 is a constant na beta. This is the thing we've learned like from the first day of differentiation.
Okay. Okay, got it.
Oh. Yeah. So anyway, Rishita and Zanvi, your answers are correct for the second part also. Now I'll just complete it. This thing I was doing first, then I'll come to the second part's answer. So this is an alternate way of doing the same thing, that just taken the 4 outside first. So this is 1 plus x square into 1. So that's that much minus x into 2x. So you're getting the same. So by taking the 4 outside early on, we're just simplifying the calculation a little bit. Okay. Now we have to find the value of the dy by dx at the point x equal to 2. So all we have to do is substitute the value of x as 2 here or here. So 4 into 1 minus 4 divided by 5 square. So that's minus 12 by 25. You can also write that as minus 0.48. So that's the slope of the tangent at that particular point, x equal to 2.
Sir, the second one you counted out the slope of tangent. So here we won't use the graph.
Yeah, I didn't ask for the graph in the question. I just asked for the value of slope of tangent. No? So I just need this numerical value, no? Minus 12 by 25.
Okay, sir.
So
Yes.
I just wanted to confirm the differentiation of x will be 1, right?
Yes, that's correct. You just use that formula of differentiation
sir.
of x to the power n. Put the value of n as 1. So we get 1, right?
Yes, yes, sir.
Okay, so these are the properties, including the advanced properties. Now, the final thing in differentiation we'll see is chain rule for what is called differentiation of composite functions. So first we'll understand what is a composite function. Then we will learn how to apply chain rule to find the differentiation of such a function.
So your screen went.
Yeah, just a second. Just a moment. Yeah, it's there now. No?
Yes.
Sir.
Okay. So a function of this type now. A function of a function is called a composite function. Basically a function of a function. So for example, I have, let's say, square root of 1 plus x square. This is an example of a composite function. Because I can say that 1 plus x square itself is a function. Okay, and therefore square root of 1 plus x square is square root of gx, which we can say is f of gx, because f is the square root function. Okay, so we are operating two things. Starting from x, first we are operating, okay, so from x we operate g on x. So we get gx is equal to 1 plus x square. And then on that we operate f, which is square root function. So we get f of gx, which is square root of 1 plus x square. So that gives us the value of y. Okay, so this kind of function is called a composite function. Okay, so I haven't come to chain rule yet. Okay, I've just explained so far that what is a composite. Yeah, so I've just explained so far that what is a composite function, and that, as you can see, is a function which is in such a way that there are two operations or two layers, or you can say one function is operated on another function. It is a function of a function. Yes.
So when we do such functions, we have to start from the innermost, like gx, and then go to the outermost thing.
Yes, yes. Like for example, now if I just ask you that, okay, I have given you the function square root of 1 plus x square. Okay, and then I ask you what is the value of y when x is equal to, let's say, 2. So what you'll do first, now you'll put 2 inside. Now, so you'll say that, okay, y is equal to square root of 1 plus 2 square. So you calculate this quantity inside. So it's 5. So now you'll say that, okay, y is equal to root of 5.
Okay, sir.
So from x, we are first operating the function 1 plus x square. So that is giving us this. And then on that, we are operating square root. So that's giving us square root of 1 plus x square. So this inner one, we are calling gx. So this whole function is becoming f of gx. F and g are just names, but the important thing is that it's one operation, and then on top of that, we are doing another operation. So there is one inner function and there's one outer function. So in the example that I have given you, square root of 1 plus x square, the inner one is 1 plus x square. Now, first we have operated the inner one on x, and then we have operated the outer one on that function 1 plus x square. So it is square root of gx, or it is square root of the function which is 1 plus x square.
So on the right hand side, that which you wrote in the red,
Yes.
y is equal to root 5. After that, what you have explained?
Y is equal to root 5. So that I was explaining just in terms of a visual picture, that how we are operating on X to get Y. Okay, so what are the operations that we are doing? Just a moment. So the operations that we are doing are in this order. That first we are operating 1 plus x square on X. On the variable X, what is the first thing we are applying? We are applying 1 plus x square. And that is our gx. And then on that we are operating what? We are operating square root function. So we are getting square root of 1 plus x square, and that is our f of gx. Is it clear now, Vita?
Okay, sir.
Okay, so this is about a composite function. Now we come to chain rule and how we apply differentiation by chain rule for any composite. Sorry?
Sir, I will write.
Yeah.
So here, instead of doing this, can we say like we raise the 1 plus x squared to half and then do it with the other formula?
But then how you will expand to the power half beta? Then we'll have to expand by something called binomial theorem. Na? And for that kind of power, you will get an infinite series, na? Because it's not like a whole square or a whole cube or something.
Okay, sir.
So unfortunately, this function is such that we cannot expand it. Instead of this, if I had given 1 plus x square whole square, na, then yeah, you could have expanded it. Or whole cube also you could expand it. But in this case, we can't expand it. Na? So
okay, sir. Thank you.
yeah.
Then, sir.
Oh. Just a moment, people. I'll join you. Yeah, so now we will understand differentiation of composite functions by chain rule. So the chain rule is a step-by-step process. It's a 3-step process basically. So given a composite function, okay, y is equal to f of gx. The 3 steps we apply are like this. Step 1 is called the substitution step. So what we do is that the inner function gx is substituted as a dummy variable. You can give it any name, but I'm naming it z over here. We can call it a, b, c, whatever, it doesn't matter. Okay. Then the second step, and of course, the moment gx becomes z, so y becomes f of z because we are replacing g with z. Okay. So that's your first step, the substitution. We substitute the inner function as a dummy variable z or whatever you call it. So the y becomes f of that particular dummy variable. So y becomes f of z because the outer function here is f. And the second step is what we call the actual chain rule step because we apply the chain rule here. So chain rule is like this, that dy by dx is equal to dy by dz multiplied by dz by dx. So this is a simple thing about ratios. You can see that I want change in y divided by change in x. So I can express it as change in y divided by change in z into change in z divided by change in x. Okay, so this is a logical step, and this particular formula is called the chain rule formula. Okay, so now we substitute that over here. So from above we can see that y was equal to what? F of z. So y will be replaced with f
But
of
t is a dummy variable.
z, whatever you call it, z or z. Okay. And z is nothing but gx. So differentiation of fz with respect to z, in short form we can write as f prime z, and differentiation of gx with respect to x we can write in short form as g prime x. And the final third step is very simple. It is resubstitution. That is, we have got the answer in terms of z so far. Now z is a dummy variable, so we have to remove it. We have to eliminate it. So we'll resubstitute z as gx. So this thing, it has to be resubstituted. So in this step, we get the final value of dy by dx as f prime of gx into g prime of x. Okay. So this is just the method which I've shown you with a general composite function f of gx. Now, whatever actual function we will differentiate using this method, in place of f and g, we will actually substitute the given formula or the given functions, but we will execute the steps exactly in this order, and that's how we will come to the derivative. Okay. So make a note of this first, then we will discuss an example problem, and it will become easy for you how to apply this.
Sir, it is an alphabet Z or it is Z sec something like you have
It's
to.
alphabet set. Some people write it like this. Okay. Some people write it like this. Some people write it like this. So I choose to write it like this. Okay.
Yeah, okay, sir.
So done.
Yes, sir. Done.
So now let's apply this to, we can start with that example question we were doing earlier. So y is equal to square root of 1 plus x square. That was our example. So here, what was the inner function? If y is equal to f of gx, the inner function was 1 plus x square. Okay. And the outer function was the square root function. Okay. Or you can write it as square root of gx first and then substitute g. Okay. So f was the square root function. So now we want to find out dy by dx in this question. So we will go by the steps of the chain rule. So step 1 was the substitution step. So in substitution, what we do, we substitute gx as z. No? So f of gx becomes f of z. Okay. So do the same substitution here. So what should I substitute as z?
One plus x square.
One.
Yes, very good. 1 plus x square should be our dummy variable. Okay. So then what does y become? It just becomes square root of z. Okay. Or that's the same thing as z to the power half. So the moment you've written it like this, you can see the whole thing has become much simpler because z is 1 plus x square, which is a very simple quadratic function, nothing difficult about it. And y is just z to the power half. That's also a very simple function. So now we have to just execute the step of the chain rule and then we are more or less done. So the chain rule is that the rate of change of y with respect to x is the same thing as rate of change of y with respect to z into rate of change of z with respect to x. So now we have to just see what is the relationship between y and z. It's written over here. So substitute that here. Okay. And what is the relationship between z and x? That's written above here. So this one we'll substitute here. Okay. Now differentiation of z to the power half will become 1 by 2 into z to the power minus half. Differentiation of 1 plus x square we've seen earlier today also, that's 2x. Okay, so this, when we simplify it a little, it's x upon root z. And finally, what we have to do, we have to remove our z from the equation.
Sir.
Yes, what
How
happened?
you derive 1 plus xy is equal to z? How you got?
No, that is the substitution. We didn't derive it. That is the method, na? Ki gx has to be substituted as z. वही तो बोला पहला step है. The inner function has to be substituted as a dummy variable.
Okay, sir. Good.
So now finally what we have to resubstitute. We have to resubstitute z as 1 plus x square. So that's our third and final step. So after resubstitution, z to the power minus half. Got it? Okay, so 2 cancels out. X upon z to the power half. That is x upon. Okay. So finally our dy by dx becomes the same thing, but we'll just replace z with 1 plus x square. So that becomes my answer. That's now the derivative.
Sir, this was wrong answer.
Sorry?
But the procedure is like this.
I didn't understand better. What was your question?
Since I'm asking you that like this only we have to write step by step the procedure.
Yes. See, the thing is, obviously in NEET or JEE, your steps will not be checked. Okay. But the thing is, if you don't write the steps now, you don't have to write each and everything in detail, but you have to do the 3 steps. Because if you try to skip one step and do directly, you are likely to make a mistake. So you don't exactly have to write like this, but at least you should write this much, that you're putting 1 plus x square as z. So y is becoming root z. So then dy by dx is differentiation of this term directly you can write. Okay. Differentiation of this term directly you can write. So this much skipping work you can do eventually. Okay. But still your 3 steps must be very clearly done in order, one after the other. You can't skip any step in between. Okay. And the kind of direct writing also I'm doing, like, don't do it immediately right now because you're likely to make mistake. Okay. So don't be in a hurry to complete the question fast. More important is make sure you don't make any mistake while doing the question. Then with practice, the speed will come. Okay. The reverse is very difficult, that you're very fast, but you're making mistakes. So then how to eradicate the mistakes? That's very difficult. But even if you're very, very slow in solving questions, but your work is perfect, you never make a mistake. Then it's just a matter of practice and you will get the speed eventually.
Sir,
Yes.
so in the step 2, the chain rule, in that the second step, you substituted the value of y as root z, and then into you substituted the value of z as 1 plus x square, right?
Yes. So those 2 substitutions are coming from the earlier step. That's how we've done the substitution.
Yes, and then we took the differentiation of root z and differentiation of 1 plus x square.
Then the next step is just application of differentiation formula.
Yes, sir.
Power formula and
Sir,
Sir, in step
yes.
2 in red color, what have you written?
It's a resubstitution. Z is equal to 1 plus x square. That's how we got the last step.
Okay.
This is how we've reached from here to here.
sir,
Yes.
why didn't we substitute the dz in the denominator as 1 plus x square in step 2?
How we'll differentiate बेटा? वो तो differentiation का step है ना. अगर मैं वहाँ पे z को 1 plus x square लिखूंगा, then how I'll differentiate the term z to the power half with respect to 1 plus x square?
Yes, yes.
Understood? Resubstitution is done in the last step. No? It's not the second step. In the second step, we are doing the differentiations. Okay? So we are differentiating y with respect to z. So what we have to substitute? We have to substitute the value of y in terms of z. So this is the thing that is substituted. Y is substituted as root z. And again, we are differentiating z with respect to x. So z is substituted as 1 plus x squared. Okay, people. So hope this question is fully clear.
So last
Yes,
one
sir.
writing.
Yeah. So with that, we come to a conclusion of today's lecture. So now with this, we have learned all the techniques of differentiation. So you will not have difficulty with differentiating any type of function using this. Okay. So next lecture, we will look at some applications of differentiation. Now that we have learned how to do differentiation of any and every type of function, then apart from slope of tangent, what else we can do with differentiation? What else we use it for? So we will see some application type of things. And of course, we'll do more practice with chain rule applications and product and quotient rule applications also.
Completed, sir.
Okay, so that's it for today, people. Thanks for attending. Wish you all the best.
Thank you, sir. Have a
Thank
good
you,
evening.
sir.
Yes, good evening to all
Bye,
of you.
sir.
Thank you, sir.
Okay, people. Good night.
Bye, sir.
Thank you, Shabashka.